introduction. And also want to thank the organizer for giving me this opportunity to report our work here. Today I will present a model for image processing. In this model is based on the low dimensionality of the patch manifold of the image. So we call it a low dimensional manifold model. This is joint work with Professor Stanley Osher in UCLA, and we drew he was a PhD student at UCLA, and now is a postdoc at the Duke University. And also my former student, Zhen Li, he's now a postdoc in Hong Kong University of Science and Technology. This is the outline of my talk. First, I will present a low-dimensional manifold model. Our model is based on the patch manifold. So first, I will give a brief introduction to the patch manifold of the image. And in this model, we want to minimize the dimension of the patch manifold. This will give us an optimization problem. And we use the split Bregman to solve that problem, optimization problem. And we find that one key step in solving this problem is to solve Laplace-Beltrami equations on point cloud. And we use the so-called point integral method to solve that equation on point cloud. And we also present some numerical results in different applications. And in this model, one key step is to solving Laplace-Beltrami equation on point cloud. And recently, we found that the PDEs on point cloud is also closely related to some deep learning neural network. So we also, and more precisely, we found that the one special neural network, residual network, can be formulated as a transport equation on point cloud. And based on this observation, we can also consider other PDEs. We get varieties of models based on PD on point cloud. And this part of work is still undergoing. So now I do not have any experimental result to present in this talk. However, I think this observation is quite interesting. Maybe it is worth to report it here also. Okay, now let's go to the low-dimensional manifold model, where I want to deal with a general image processing problem. Usually, one image processing problem can be formulated in this way. Here, F is the original image we want to reconstruct. Phi is a measurement operator. It may be different in different applications. For example, in the denoising problem, phi is an identity operator. And in painting problem, phi may be some subsample operator. And the epsilon is a noise, and the B is a measurement we have. And we want to recover the original image F from the measurement B. Usually the measurement B only contains some part of the information of the original image F. So to recover the original image F, we need some prior knowledge on the image to give us a regularization term to help us to pick up the best reconstruction of the image. Our low-dimensional manifold model also provide regularization. In this model, we use the dimension of the patch manifold as a regularization to help us to construct the original image. Okay, now let's go to the patch manifold. The patch is very simple. Patch is just a small piece of the image, small piece of the original image with fixed size. For example, let's take the size of the patch is 10 by 10. And for each pixel in this image, we can take that pixel as the upper left corner pixel of that patch and take a patch with 10 by 10 around it. And for each pixel, we can get a patch, right? So totally, the number of patch is the number of pixels in this image. For example, let's say the resolution of this image is 1,000 by 1,000. So totally, after taking patch, we have 1 million patches. And each patch is 10 by 10, right? Then we can stretch each patch to a 100-dimensional vector. And this 100-dimensional vector gave us a point. Oh, sorry. Which one? Okay. And this we can stretch the patch to a 100-dimensional vector, and this vector gave us a point in 100-dimensional space, right? Then we have 1 million points in 100-dimensional space. Since this point is a patch of an image, it must have some structure in this 100-dimensional space. It cannot be randomly distributed in this high-dimensional space. So usually people found that this point, this cloud of point, concentrates around a smooth manifold embedded in this high-dimensional space. And this manifold is this underlying manifold is called patch manifold associated with the image. And one important property of this patch manifold is that usually its intrinsic dimension is much lower than the embedded Euclidean space. In these two papers, there are very excellent demonstration of the low dimensionality of the patch manifold. And here I'll just borrow some simple examples from these two papers to show that the intrinsic dimension of the patch manifold is much lower. Okay, first let's see if the image is smooth, is a smooth image, and since the patch, each patch is a small piece of this image. So locally, we can approximate this patch by Taylor expansion and only keep the first two terms, the constant term and the linear term. And using this Taylor expansion, we know that to determine this patch, we only need 3 parameters. This constant, and there are 2 parameters in this gradient, since the image is a 2-dimensional function. So, which means that we only need 3 parameters to determine, approximately determine the patch, each patch associated to the smooth image, which means that the patch manifold associated to the smooth image, its dimension is approximately 3, right? Now let's consider another example, the cartoon image with a 0 and 1 intensity. And so the patch, to determine the patch, we only need to determine the location of the interface between the 0 and the 1, right? Locally, we can approximate the interface. If we assume the interface is smooth, then locally we can approximate this interface by a straight line. And to determine the location of this straight line, we only need 2 parameters: the orientation and the shift along the normal direction, right? Which means that for a cartoon image, the dimension of each patch manifold is approximately 2, right? And for the text image, we assume that the text image can be approximately in this way. Here, the envelope function A and the phase function theta are both smooth functions. As we mentioned previously, for a smooth image, the patch manifold is the dimension is approximately 3. Now we have 2 smooth functions. So the total dimension is approximately 6, right, for the texture image. So no matter in which case, we can see that the dimension of the patch manifold is much lower than the embedded Euclidean space. In our example, the dimension of the Euclidean space is 100. And in these 3 examples, the dimension is 3, 2, and 6, right? Based on this observation, one natural idea is that we want to minimize the dimension of the patch manifold to pick up the image. We want to look for an image F such that the patch manifold has the lowest dimension. This idea just gave us this formally gave us this optimization problem. However, this problem Okay. However, this problem is not well-defined. It's not computable in this stage, since we do not know how to compute the dimension of the patch manifold associated to an image with a given image. Right? We need to give a formula to compute the dimension of the patch manifold with a given image, right? To make this formal optimization problem computable in mathematics. Fortunately, we have a very simple formula to compute the dimension of the manifold. By using very elementary differential geometry, we can get this simple formula. Here, alpha j is the so-called coordinate functions. It's very simple. Since the manifold is embedded in a Euclidean space, or d-dimensional Euclidean space, so for each point x in the manifold, it has d coordinate in the Euclidean space, right? So then the alpha I is just defined as the ith coordinate of x in the Euclidean space. It's a very simple function, right? Then the dimension, we find that the dimension of the manifold can be given in this way. Here, gradient m is a gradient in the manifold, not in the Euclidean space. And using this simple formula to compute the dimension of the patch manifold, we have this optimization problem. This is at least well-defined in mathematics and computable, right? And here we need this constraint. This constraint just to guarantee that here PF is the patch set. All the set consists of what's wrong? Okay. Here, PF denotes the set of all patch from extract from the image F. So this just means that the M is a patch manifold of the F, right? Then we get this optimization problem, and we want to solve this Okay. Oh, switch to the HDMI. Okay. Okay. Okay, thank you. Now we want to solve this optimization problem. However, this problem is highly nonlinear and non-convex. So actually, we do not know any algorithm can solve this optimization problem. Here we just use very heuristic iterative algorithm to formally solve it. The idea is as following. Notice that the most complicated part in this problem is here, is a gradient operator on M. It is related to the structure of the manifold. So the manifold is also one object we want to optimize. So, however, suppose if M is fixed with given M, then this operator becomes a linear operator, right? And essentially, this optimization problem becomes a linear least square problem. And this just the idea to solve this problem. We just update M and image F iteratively. First, we fix M, update F, and then we update M from the new F. So this idea gives us this iterative algorithm. In the first step, we fixed M to be the current, to be m at n step. And we want to update f, and then we update m from the given f. This step to update m is very simple. Just take a patch from the new f. We get the new sample of m. Right? So the most difficult part is to solve this optimization problem. Here, we have a new constraint. This constraint just comes from this constraint. The new we want to make sure that the new m is the patch manifold of the new f. Okay. Next, we need to solve this constraint optimization problem, and we use split the Bergman to solve it. First, we use a Bergman iteration to deal with this equality constraint, and we got this iterative algorithm. In this step, we need to solve unconstrained optimization problem. And then we use the split idea of the split Bergman to solve f and the coordinate function separately. And we got this algorithm. In the first step, we solve the coordinate function. In the second step, we solve f, and we update this augmented variable d. Let's see, the last step is very simple, just some algebraic computation. And the second step is standard least square. And in some case, with a simple measurement operator phi, it even has an explicit solution. And so the most difficult part is to solve this unconstrained optimization problem. Okay, now we summarize our algorithm here. Remember that we have two iterations. The outer iteration is between the manifold M and the image F. And the inner iteration is a split Bergman iteration to solve that optimization problem for the image F. And then next, we will focus on this optimization problem. In general, we want to solve the optimization problem in this form. Here, V is a given a vector. So usually, notice that here, this optimization problem is still in the continuous form. Before solving it, first we need to discretize the gradient, this gradient operator on the point cloud. Usually, people use so-called non-local gradient to approximate the gradient on the point cloud. The non-local gradient is defined in this way. Here, W is just the kernel function, which is given. One often use the kernel function is just the Gaussian function. And if we use this non-local gradient to discretize the gradient operator, we get this discrete optimization problem. And we all know that the solution of this problem can be given by solving this linear system. So now we have a complete algorithm to solve that problem. Now let's see some results. Here is the original image of Barbara, and we take a 10% subsample, random subsample of this image, and we want to recover this image from the 10% subsample. This is a result given by the algorithm based on the non-local gradient. Actually, honestly, the result is not very good. Okay, let's zoom in this area, this red box area. This is the original image. This is a subsampled image, and this is a recovered image. We can see that in the recovered image, there are many isolated pixels which are inconsistent with the background. And if we compare these two images, we can see that all the isolated pixels are sampled pixels, which means that the solution given by the algorithm is not continuous at the sampled pixels. In these pixels, we actually know the intensity at these pixels. So this means there must be something wrong in our algorithm. Now we use another method, which is called Poynting integral method, to solve that continuous optimization problem. First, we still keep this optimization problem in the continuous form. And using standard variational approach, we know that the solution of this optimization problem can be given by solving this PDE. And now we need to solve this PDE, Laplace-Beltrami equation, on the point cloud, since the manifold M is sampled by the patches of the image. And we use the so-called Poynting integral method to solve it. The key ingredient in the Poynting integral method is this integral approximation. The idea is that we approximate the differential operator by integral operator. And in the integral operator, there is not any differential operator inside. And in the point cloud, it is much easier to discretize integral operator than discretize differential operator. Right? So we can prove this integral approximation for Laplace-Beltrami operator on a manifold. Here R and R bar are just given kernel functions, and they have this relationship. We can do some error estimate to prove that the error is of the order of t to the power of 1/4. And maybe I'll skip the analysis due to the limitation of time. In the analysis, we just use the Taylor expansion and the integration by part, which is very straightforward. In the manifold, the computation is a little more complicated and tedious, but in the Euclidean space, it's very simple. Okay, by using that integral approximation for the Laplace-Beltrami operator, we can transfer this Laplace-Beltrami equation to an integral equation on the manifold. Just multiply the kernel function on both sides of this equation, and using that integral approximation, we get this integral equation on manifold. And then we just discretize this integral equation. This discretization is very simple. We just replace the integral by summation. Now we have this linear equation to approximate the Laplace-Beltrami equation on the point cloud. We can also rewrite in a matrix form, more concise. Now we have our algorithm based on the Poynting integral method. We just replace the non-local gradient by the Poynting integral method. Nothing. The else part just keep the same as the previous algorithm. So this is the result. This is the image of both, and we also take a 10% random subsample. And this is the result reconstruct by our algorithm. And this is the result given by another dictionary learning based algorithm. It's called BPFA. And visually, we can see that our result is better. We preserve the edge more sharp. See? And it is also better in PSNR. This is the construction of the image of Barbara. Remember that for the image of for the method based on non-local gradient, we have many inconsistent pixels. This is the result given by the new method. We can see that these inconsistent pixels all vanish. Okay, now let's see the difference between the Poynting integral method and the non-local gradient based method. we both want to solve this Laplace-Beltrami equations on point cloud. However, notice that in these equations, besides we need to discretize the Laplace-Beltrami operator, of course. However, we also need to discretize these delta functions, right? Since the delta function and the Laplace-Beltrami operator are in the same equations, their discretization must be consistent with each other. Notice that in the non-local gradient-based method, the Laplace-Beltrami operator is discretized by these kernel functions, and this delta function is discretized by simple discrete delta function, the 0, 1 function. However, these two discretizations are not consistent with each other. In our algorithm, we use the same kernel function to discretize both of the Laplace-Beltrami operator and the delta function. So we can also prove that our algorithm converge to the right solution for the Laplace-Beltrami equation on the point cloud under some assumptions. Okay, now let's see some other examples. This is actually the solution of some PDE, the plasma PDE. So it has a very complicated structure, some small-scale structures inside. Actually, maybe this describes some turbulence. And we take 10% subsamples from this solution, and this is the reconstruction we get. As we can see, even the small-scale structures is well recovered. Okay, this is another application. This is an image of some biological tissue. I got this image from a professor in medical school of Tsinghua University. Each light spot is a cell in this tissue. And in their experiment, to get this picture, this image, for each pixel of this image, they needed to apply a beam of laser on the cells to get the intensity of that pixel. So to get a high resolution image, they need to put a lot of laser beams on the cells. And so many laser beams will kill the cells. So before the experiment, the cells are alive. And after the experiment, they are dead. So the people in the medical school, they want to keep the cells alive during the experiment. Then they can take pictures in the growth of this to observe the growth of the cells, right? So one direct way to keep the cells, one possible way to keep the cells alive is to reduce the number of laser beams applied on the cells. So we just do this test. This is the original image, high resolution image. And here we take 20% subsamples, random subsamples from this image. And this is a reconstruction we get from this 20% subsamples. And actually, that professor in the medical school said this result is better than he expected. Okay, we also applied our method on the hyperspectral image. The hyperspectral image is essentially 3D data. Besides the two spatial dimension, it also has a dimension of waveband. In this test, we have 162 waveband. So since between the different wavebands, it has a lot of redundancy inside. So in this example, we can get good reconstruction from even lower sample rate. Here we only use 5% samples of the original image, and we get the reconstruction is pretty good, I think. I only saw the 10th band of the data. Totally, we have 162 bands. Okay, we also apply our method, this low-dimensional manifold model in seismic image denoising. This is the original image, and this is a noised image, and this is the result given by the method based on Fourier transform. We just apply the low-pass filter on the image. The result is not very good. This is a non-local mean method, and this is a method based on a curvature transform. And this is our method. As we can see in the PSNR value, these three methods, the difference is very small, right? However, visually, our method seems to preserve the structure better, especially in this circle enclosed area. Okay, next thing I want to say is that our low-dimensional manifold model also applied in the matrix completion problem. A widely used model in the matrix completion problem is a so-called low-rank model. They assume the matrix we want to get has a low-rank structure. The rank is just if we take each column as a point in the high-dimensional space, and the rank is just the dimension of the linear space spanned by this point, right? So in the low-dimensional manifold model, we just generalize the linear space to a curved manifold in the high-dimensional space. Then, in this case, the rank becomes the dimension of that manifold, naturally. Right? So our model also applied for the matrix completion problem, and we also did some tests on this, on the matrix completion problem. We found that the result is comparable. This is a rank. This is a measurement of the quality of the completion. The higher the better. So this is a result given by a classical method based on single value decomposition. We can see that the result is comparable. However, in our method is much faster than the single value decomposition based method. Okay, now let's go to the second part of my talk, the relation between the PDEs on point cloud and some deep learning neural network. Let's begin from a special neural network, which is called a residual network, RESNet for short. It was proposed by a research group in Microsoft in 2015. It was posted on arXiv in 2015 and published in 2016. Now it already has more than 3,000 citations in Google Scholar citation. So this is the building block of the RESNet. I extracted this image from this paper, and as we can see, this is an input vector x. After it goes to this building block, this unit, it separates to two branches. And in this branch, it directly goes to this addition operation. And in other branch, they apply many operations, the batch normalization, the RELU activation, and this is just the convolution operator. And it repeats these operations again, and added it to the original input vector. And we can summarize these operations in this formula. Here, xn is the input, xn plus 1 is the output. And the xn is, in this operation, xn, the input xn is added to the output of these operations. Right? In this operation, we have these three operations. Here, A is just a composition of the RE-LU activation function and the batch normalization operation. And we have this simple formula to describe this unit in the neural network. And in the RESNet, many of these building blocks are connected sequentially to form a network. And at the end, one output layer is attached to get the output value. And now let's see what's going on in this neural network. Here, XR0 is an input vector from the training set. And after each layer, it was changed according to this formula, right? And at last, it was passed to the output layer to get the output value at this point. And since the input vector is in the training set, it has been already labeled as a given value. So in this network, we want to make the output value is close to the given value in the training set. And in this way, we want to get the parameters inside this network. Maybe here, some people already get the relation between the neural network and the PDEs. Now let's rewrite it in a more familiar form. We just this is Tn is just a notation to denote the layers of the neural network, and as we can see, this formula is nothing but the forward Euler discretization of the characteristic equations in the transport equation. It's actually, in this RESNet, it's actually one particle is transported by the velocity field given by V bar. And at the end, it is this value is given by the terminal value given by the output layer. So right here in a continuous form, the RESNet is actually can be formulated as a transport equation. Here V is a velocity field which is modeled in this way in the RESNet. And in RESNet, this transport equation is solved along the characteristics. And we know that along the characteristics, the value of U is not changed. So we get the terminal value from this terminal condition. And initially, since in the training set, the data has been labeled by some given values, and we want to the output value is equal to the initial value, which means that the RESNet can be formulated as this control problem of transport equation. In the transport equation, the terminal value is given by the output layer. And the initial value is also given by the labeled value in the training set. We want to solve a velocity field V such that the initial value is transported to the terminal value by this transport equation. So this is just the control problem of the transport equation. And the velocity field has this model. It is modeled by the convolution operator and the so-called activation functions. And now we can see that the RES net is nothing but the transport equations, and the transport equation is solved by the characteristics. And the velocity field is modeled in this way, and the terminal value is given by the output layer in the RES net. And the initial value is given by the labeled data in the training set. So we can, in this 5 components of the RES net, the initial value is given by the data. We cannot change. However, other 4 components, we can choose by ourselves. So we can use our numerical method to solve the transport equation, not only the characteristic method. And we can also choose our terminal value and our velocity field, and even we can consider other PDEs besides the transport equation. For example, we can choose a better terminal value. In the neural network, they usually use a very simple output functions, some sigmoid function like that, very, very simple, easy to compute. However, that output function is unrelated to the data. So one idea is that we can use some better terminal values to approximate the data, and then we hope that then the convergence may be much faster and easier. One possible way to get the terminal value is by so-called weighted non-local Laplacian. We can solve a good interpolation on the point cloud in this way, and we can use this function, the solution of this function, as the output value, so the terminal value in that control problem of the transport equations. And also, we can use other numerical methods to solve the transport equation, not only the characteristics. We know that there are many numerical methods based on Eulerian grid to solve the transport equation. However, our original transport equation is defined on the high-dimensional space, Rd. Pd is a very large number. To solve it in the Eulerian grid, it is impossible. So we need a lot of grids to discretize the high-dimensional space. However, this data set, we do not need to solve the transport equation over the whole d-dimensional space. We only need to solve it in the data set. The data set must have some structure. It must not fill the whole d-dimensional space. So in this sense, we only need to solve the transport equations in the manifold spanned. Usually, we assume that the data set lies in a manifold embedded in the Euclidean, low-dimensional manifold embedded in the Euclidean space. Now, we only need to solve this transport equation on a low-dimensional manifold. And in this, also the initial value and the terminal value are given. Now we can use some numerical method to solve it. However, in this case, we need to solve this equation on the point cloud, since the sample of the manifold M is given by the data. It may be unstructured high-dimensional point. So we need to solve this on a point cloud. And another idea is that in this model, here we need to compute a high-dimensional velocity field. V is the dimension of V is d. D is a very large number. We can also, for example, if we assume that this velocity field is given by some potential functions, then that transport equation is transferred to this equation. And now we only need to compute one scalar function instead of a d-dimensional vector field. So the number of degree of freedom is reduced significantly. And we can formulate this control problem. We want to minimize the difference between the output value and the given labeled value. And we also want to make sure that the potential function is smooth. And here the small u is a solution of this partial differential equations. And we can also consider another function, another equations. For example, if we denote v bar as the vector v dot n is defined in this way. It's just the direction of the gradient of u. And then the transport equation is rewritten in this Hamilton-Jacobi equation. And in this case, we also need to compute a scalar function instead of the high-dimensional vector field. And we can formulate this control problem. We can also formulate the control problem for the Hamilton-Jacobi equation, right? We can even consider to add some diffusion on the equations. Since we know that the transport equation has some stability, instability issue in the numerical method, we can consider to add some diffusion on the transport equation to stabilize the computation of the equation. Then we get this control problem based on the Fokker-Planck equation. We can also add the diffusion into the Hamilton-Jacobi equation to get a corresponding control problem. We can even consider the steady equations, steady Fokker-Planck equation. We just want to get the potential functions u. We can formulate this control problem to compute the potential u such that this functional is minimized. Okay, here just present some ideas between the PDE model and some deep learning residual network. Okay, let's summarize. Here I present a low-dimensional manifold model for a general image processing problem. We use the dimension of the patch manifold as a regularization to construct the image. And we use the so-called point integral method to solve the equation on point cloud. And we also find some relationship between PDE and deep learning. And we propose some possible PDE model for the residual network. Okay, thank you.
Thanks for the talk. Are there questions?
Well, in the first part, when you consider patches, you assume that they form some kind of manifold.
Yeah.
Well, what happens if it's not manifold, but I don't know, union of two planes or something else? How can you be sure that it is actually?
It's just an assumption. And the patch manifold is not a rigorous definition in mathematics. It's just some concept to help us to understand the image.
Yes, but it may be much more complex that
Yeah. Course.
It's just a hypersurface, right?
Actually, our model admits the patch manifold is not a single manifold. It's a union of many different manifolds. For example, one image, it may have a cartoon part or texture part or smooth part. For each part, it has each corresponding manifold. And the patch manifold of this image may have different components. Different components corresponding to different manifolds.
In the last part, is there any reason you can assume V is a potential?
It's just an assumption. I don't know. So there are many possibilities. It's many problems we need waiting for addressing. So
there must be a reason if you can assume it is a potential. Also, the f function. So what's the value of the f function?
Value of f function. So f function is a
T are the gxi are the known labels. Right.
Yeah, known labels.
Those might be 0.
Yeah.
So
The f is a given output function in the neural network. Usually they use very simple the sigmoid functions. They just want to transport. That simple output function is very easy to compute. They just want to find the velocity field. From the point of view of these transport equations, they just want to find a velocity field to transport these simple functions to the given at the point in the training set. They transport this output function to the given values.
What is f for general learning?
For general learning, just some 1 over some exponential based on exponential functions. Just a combination of several exponential functions.
It can be arbitrarily given, or what's the reason to choose the f in that way?
It can be arbitrarily given, but in the neural network, they often choose several very simple output functions. Here, I just propose to use more complicated output functions to well initialize that model.
Okay, I suggest we postpone further discussion to the coffee break.